Hello students, so this is my third lecture on nanocomposites. I discussed about mixed transition metal oxides in my last class. In continuation to that, I will be talking about another, it's not mixed but it is another transition metal oxide, and which is zinc oxide, which is a highly technologically important material because it has got a high refractive index, it has got high thermal conductivity, it is biocompatible, etc. And so that's why it has got a lot of applications. For example, it is used in electronic devices, it is used in biomedical applications for treating of cancer, and it is also used in photocatalysis. It's basically an N-type semiconductor. It's got a band gap of about 3.3 to 3.4 electron volt. What we will discuss here is how we can further improve the performance of this zinc oxide. Now, an effective way of improving the performance is to dope it with another metal ion. So we have chosen aluminium to dope in zinc oxide. Now the reason aluminium was chosen is this oxidation state of aluminium is +3, whereas in case of zinc oxide the oxidation state of zinc is +2. So whenever we are doping a higher oxidation state metal, the electron concentration will increase. This may cause a severe change in the electrical as well as the optical properties. Now, another thing that we have to keep into consideration is the size of the metal ions. Aluminium is having a size of 0.53 Armstrong, whereas Zn+2 has a size of about 0.74 Armstrong. So if we have if these are the Zn+2 ions, and if we replace one of the Zn+2 ions by say a smaller Al+3 ions, so to make up the valence space, the nearby ion will squeeze, so this will cause a compressive lattice strain in the lattice. Now this lattice strain will get reflected in the XRD diffraction pattern. So this is your zinc oxide peaks, which happens to be approximately around 34. We get three main peaks. This is around 34 and this is around 36. There may be some alterations in the Bragg angles. It's not exactly what I've written, but it is close to these angles. Now doping with an aluminium will cause a peak shift like this, but when it moves towards the higher Bragg angles, this indicates a compressive strain. Now in the lattice, as we have a sufficient number of aluminum ions, so these aluminum ions, they tend to move around the different lattice sites. For example, if we have a aluminum ion at position A and we have a vacant site at position B, so definitely the aluminum ion will try to move to the vacant site. But to do that, it has to cross a potential. There is a potential barrier between the host, this we call as the host, where the aluminum is initially present, and this is the vacant site, and there is a potential difference E between A and B. Now this potential difference is minimized if we put electromagnetic wave, for example light. So putting a light, what it does, it increases the potential at A, whereas it decreases the potential at B. So that makes the aluminum or the impurity ion movement much easier. That is why under UV light the zinc oxide becomes more active, and it can be used for treating cancers or damaged cells, or it can be used in photocatalysis. Now instead of using an electromagnetic wave, what we can do, if you want to increase the number of ions, or if you want to increase the movement of this impurity ions in the lattice, we can dope it with another metal ion. That's what we are doing right now. So a higher concentration of aluminum ion will cause a higher electron concentration and higher movement of electrons and holes. That will actually cause the improved photocatalytic and antibacterial property of zinc oxide. Now coming to the optical properties due to aluminum doping. Aluminum doping causes a significant reduction in the band gap. Now the absorption spectra that we obtained, and if we plot the band gap diagram, or we plot alpha H mu versus H mu, we see that if this is 1% aluminum doping, this will be say 5% aluminum doping. So you can see there is a significant reduction in the band gap. Another thing that is important, or that is interesting to see, is that increase in the concentration of the aluminum atom causes deviation from linearity between alpha H nu square and H nu. So if the curve is linear, it means that there is a direct transition taking place. Deviation from linearity means the aluminum ion impurities is finding other diffusion paths, and it is deviating from non-linearity. Okay. So due to this short circuit diffusion, we can call it a short circuit diffusion. Now the diffusion will again is dependent upon certain factors. The diffusion coefficient is equal to Fp lambda to the power 5, where Ft stands for probability of forward hopping as it moves, or probability of forward movement from a host site to a vacant site, and lambda is the interplanar spacing. So apart from this, the diffusion will also depend upon E divided by Tm, where E is the potential difference between A and B, as I have already mentioned. Between the host and the vacant site, there is a potential difference, which is E. This is E, and T stands for the melting temperature. So these two factors are also governing the diffusion of the impurity atoms, especially the aluminum. Now, after a certain concentration of doping, what we observed that we doped aluminum for 0.5%, 1%, 2%, and 5%, and we found out the particle size. The initial particle size was 12 nanometers for 1% doping. For 0.5% doping, which changed to 32 nanometers, which changed to 39 nanometers and 41 nanometers. So there is an increase in the particle size with aluminum concentration, and the particle size is of course found from this equation, which is very well known equation, Schiller's equation. The band gap obtained from optical studies were 3.27 electron volts, 3.19, 3.18, and 3.15. So we can see that there is an increase in particle size and there is a decrease in band gap. So we can explain it by the fact that between the conduction band and the valence band of zinc oxide, due to aluminum doping, there is an extra impurity energy levels being created. So that is why there is a decrease in band gap. So initially the band gap used to be like this. Due to defect creation, the band gap has reduced to like this. This is the explanation for the reduction in band gap. The increase in particle size explanation is the short circuit diffusion path, which we have already explained in my previous slides. So due to this short circuit diffusion path, what happens is that the particles, whenever we have small crystallites, the increase in particle size is of course due to coalescence of these crystallites. So if we are introducing short circuit diffusion paths, so more number of diffusion of atoms can take place, and that's why the coalescence and increase in particle size can occur.